If you peel back the screen of a modern computer, you'll find a system that operates exactly like a highly efficient commercial kitchen. To see how it works, we can look at the hardware. These are the physical parts you can touch: the keyboard, the screen, and the chips inside. In our kitchen, the hardware is the appliances, the pots, and the pans. But an oven won't bake anything without a recipe. That's where software comes in. Software is the set of written instructions telling the hardware exactly what to do. Next, we need ingredients. In computing, we call this data. Data is just a collection of raw, unorganized facts, like a random string of numbers. On its own, it doesn't have much use, much like a pile of raw flour and eggs sitting on a table. When you follow the recipe to mix and bake those ingredients, you get a finished cake. In a computer, when data is organized and processed, it becomes information. It finally has a meaningful context we can understand. A computer's job is to use hardware to execute software instructions, turning those raw data ingredients into meaningful information. Every process starts at the input stage. When you type on a keyboard, you are essentially handing an order to the kitchen. The computer takes your interaction and converts it into binary code, a series of zeros and ones that the machine can read. This chart splits computer storage into two branches. Secondary memory, like a solid-state drive, is the massive main pantry, holding files safely for the long haul. Primary memory, or RAM, is the fast kitchen counter where the system moves programs to work on immediately. But there is a trade-off. The data on this kitchen counter is only temporary. If the power cuts out, anything left on the counter is instantly wiped clean. Only the supplies tucked away in the permanent pantry stay safe. Efficient computing is a balancing act. The system relies on small, lightning-fast memory for active work and vast, permanent memory for long-term preservation. This maps the central processing unit. As the machine's brain, it acts as head chef. The control unit directs data flow like a traffic cop, while the arithmetic and logic unit acts as the sous chef, performing the actual math to turn input into results. All this hardware needs management. Operating systems, like Windows or Android, act as system software to keep the kitchen running. Meanwhile, application software, like a web browser, are the specific tools you use to get a job done. Once the processing is complete, we reach the output stage. The computer translates those millions of digital calculations back into a format that you can actually see and use. This output is delivered in two ways. It can be a digital version on a screen or through speakers, or it can be a physical version, like a document from a printer. The entire system, input, storage, processing, and output, works in a synchronized loop. It's a chain of hardware and software working together to produce the result you asked for. This map shows the path data takes through a machine. We collect, clean, input, process, and present information. This logic of refining input into a useful result allows a computer to handle everything from simple math to complex simulations. But as we upgrade to faster and faster machines, we create a growing mountain of electronic waste. Discarded devices are a mix of hidden value and hidden danger. They contain precious metals like gold and copper that can be recovered, but they also contain toxic substances like lead and mercury. When old computers are simply buried or burned, those toxic chemicals can leak into the soil and water, causing long-term damage to the environment. This is why responsible recycling is important. By using certified centers and manufacturer take-back programs, we can recover valuable metals and keep hazardous materials contained. Computing isn't just about the logic happening inside the machine. It's also about managing the physical footprint those machines leave behind.